The second talk will be by Riccardo Brasca from Université Paris-Cité. I don't know which Paris-Cité.
Yeah, we changed the name recently.
So what is that, 6, 7?
Yeah, it was Paris 7.
7, okay, thank you. And he will talk on Fermat's last theorem for regular primes in Lyon.
Okay, so thank you very much for the introduction and the invitation. I'm very happy to speak in this conference. So I'm sorry to not be present in person, but 2 weeks ago I had the bike accident and I broke my ankle, so I have to stay at my place. But I mean, at least I'm able to give the talk online. So as the title of my talk suggests, I'm going to speak about a project whose goal is to prove Fermala's theorem for regular primes in Lyon. So this project has two main goals. So first of all, of course, the first goal is to verify the proof of Fermala's theorem for regular prime exponents. And I will recall in 2 minutes the statement of Fermala's theorem and also what a prime exponent is, a regular prime is, sorry. So this is a nice piece of mathematics, but in my opinion, this is not the most important goal of the project. A more important goal is really to develop algebraic number theory in MATLib. So MATLib is the mathematical library of Lyon, where all the results about undergraduate mathematics and also a lot of graduate mathematics are. So, and as Patrick said, we are more than 200 people developing MATLib. And so proving Fermala's theorem for regular primes is really an excuse to develop algebraic number theory in MATLib. Indeed, we are not at all trying to prove the result as fast as possible, but we are rather trying to really develop the theory in a good generality. And we hope that when the project will be finished, maybe this year or next year, people will be able to use all the library we developed. So in my opinion, this is really the most important part of the project. Proving a theorem is just an excuse. It's a nice goal because, I mean, we will be happy when we will see goal accomplished, but the real goal is to develop MATLib, so to develop formalized mathematics. So if you are interested in seeing the actual code, you can just go to GitHub or look for FLT regular on Google. And this is the repository. So all the code is there. But as I said, since we are trying to move everything to MATLib, you also should check the number theory folder in MATLib. Indeed, a lot of results are already moved to MATLib, since we are trying more or less to move in real time. So when we prove something in good generality, we try to get accepted into MATLib as soon as possible. Okay, so this is a joint work. So everybody is welcome to contribute. So it's joint work with the MATLib community. We are, I think that more than 15 people that have wrote some line of code, but especially there are people that contribute more than others. So the most important contributors are Alex Best, Chris Burbeck, Eric Rodriguez, and myself. So Alex and Chris are mathematicians. I think they are both postdoc in mathematics, both postdoc, but Eric is an undergraduate student. So it's quite amusing to collaborate with an undergraduate student. He's learning the math at the same time as he's formalizing it. So it's a rather an interesting process. And I also think this is a good thing about formalized mathematics, that it's possible to collaborate with undergraduate students. Indeed, Eric is expert in Lyon. It doesn't know really well the math, so we're really collaborating with him, and it's a nice experience. So if you want to contribute to this project, you can just write us on Zulip. So Zulip is the Lyon chat. You can find it on Google. There is a dedicated stream about the FLT regular project. So if you are interested in contributing, you can just write us, and there is work for everybody. So there are a lot of small lemmas to prove. So you don't need to be an expert in Lyon to start contributing. And also, if you are interested in Lyon in general, you absolutely have to go to Zulip. I mean, all the discussion about Lyon happens in this chat. So all the experts are there, and all the people working on Lyon spend their days on Zulip, essentially. Okay. So this was the introduction. So let me start recalling what Fermala's theorem is. So this is a very well-known statement. You probably all of you already know it, but let me just recall that the statement is the following. So let n bigger than 2 be a natural number. Then the equation x to the n plus y to the n equals z to the n has no non-trivial solution in z. So what is a trivial solution is a solution where one of the three variables, at least one of the three variables is a 0. So you see that, I mean, for example, 0, 0, 0 is a solution, 0, 1, 1 is a solution, and 1, 0, 1 is a solution. So these are the trivial ones, and Fermala's theorem says that these are the only one if n is at least 3. And of course, if n is 2, this is false. I mean, there are all the Pythagorean triples. So this has been conjectured by Fermat in the 17th century. So he said that he had a nice proof, but this is probably not true. So it has been finally proved by Weiss and Taylor in 1995, after more than 300 years and a lot of failed attempts. So now it is a fully proved theorem. But the proof, it's really a 20th century proof, meaning that it used a lot of advanced mathematics. So it would be nice to formalize the full proof, but it's something that is currently undoable because the proof use a lot of results in several areas of mathematics. For example, it used a lot of results in number theory. Indeed, what Weiss and Taylor proved is a statement about modular forms that was known to imply Fermala's theorem. So to state what they really proved, I'm not talking about the proof. Even to state the theorem, we need to develop a lot of stuff about modular forms, and they also use a lot of algebraic geometry in the language of schemes and representable functor and a moduli space and so on. So we need a lot of algebraic geometry, and they also need some harmonic analysis. So we are really, really far from being able to even state the theorem Weiss and Taylor proved. So and we are the proof, it's even more difficult, of course. So it's currently unreasonable to formalize it. Maybe in 10 years, it will be a nice goal, but currently is a science fiction because we are missing too many prerequisites, too many stuff, too many results. Okay, so this project, the goal of this project is to concentrate on a special case. So we are not treating all exponents, but we are treating the exponents that are regular primes. This is very nice because to be able to prove this theorem, we have to develop algebraic number theory, and at the end, these theorems will be needed even if one wants to prove the full theorem. So in some sense, we are working towards the full theorem, even if today is still science fiction. So first of all, there is one case that has to be treated separately. It is the case for n equal 4. So this was known to Fermat itself. So the theorem is true if n equal 4. The proof is not very difficult. It's rather is an infinite descent, and it's a rather elementary exercise in number theory. So since the theorem is known for n equal 4, we can reduce the theorem to a prime exponent. Even if the exponent is a power of 2, then the theorem is a consequence of the theorem for n equal 4. And if the exponent is not a power of 2, one can just write the exponent n as p times something, where p is an odd prime, and then just writing x prime equal to x to the n divided by p, we can reduce the theorem to a prime exponent. So essentially, to prove the theorem, it is enough to prove it for all primes. So the proposition, so the Fermala's theorem for n equal 4 is already in MATLAB. I mean, it was already MATLAB before we started the project. So this is the statement in MATLAB. So here I'm showing you the actual code in MATLAB. So this theorem is pretty readable, but maybe later on, I don't want to cheat, so I will always show you the actual code. Sometimes there are things that are not so readable. Let's just ignore them if the things became too complicated. But so you see that this one is very easy. So theorem, so not Fermat 4 is the name of the theorem. We can choose it, of course. So let A, B, C be integers. Then let's suppose that A is different from 0. Let's suppose that B is different from 0. Then A to the 4 plus B to the 4 is different from C to the 4. So this is pretty readable. I mean, very readable, I would say. So every time you see this colon, just read belongs. So this is because the foundation of Lyon is type theory, but this really means A, B, C belong to Z. Okay, and the proof of the theorem is in Lyon is not very complicated. It's less than 300 lines of code. I mean, I'm not going to show you the proof, but it's public, so you can look it. It's on GitHub. It's really readable. It's really the same proof as we do in our number theory courses. So it's really nothing complicated. There are no surprises here. So I don't know if the corollary is in MATLAB or not, but I'm sure that it would take half an hour to formalize it. I mean, even less probably. So the corollary is essentially formalized. I'm sure there are no problems in formalizing it. Okay, so now the theorem is true for n equal 4, and so it is enough to prove it for prime exponent. So here is Kummer's idea to prove the theorem. So let's suppose that Z to the P is equal to X to the P plus Y to the P. Then we can just write the right-hand side as a product. So we have Z to the P equal X plus Y times X plus ZPY times blah, 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 where ZP is a pth primitive root of unity. So here I choose e to the 2 pi I over P. And of course, this equality it doesn't make sense in Z, of course, because ZP is not an integer, but it's true in this ring in Z of ZP. So this is the smallest subring of C containing this root of unity. And so if you are not a number theorist, you can maybe think that this is a weird thing to do. But the point is that now this is a product, and so you have a pth power that is equal to a product, and this is much more treatable than a pth power that is equal to a sum of pth power. So this is a really standard technique in number theory to try to write a sum as a product to simplify stuff. I mean, I guess that this has been invented to solve Fermala's theorem, but nowadays it's really a standard technique. Of course, there is a price to pay, and the price is that now we have to work in this ring. So this ring is much more complicated than Z. At the beginning, we can think that the properties are more or less the same, but unfortunately, from a number theory point of view, the ring is really much more complicated. For example, there is a notion of prime elements here and irreducible elements here, but these notions are not well behaved. I mean, are not as well as in Z. So the theory is really more complicated. So the idea is that if we have this equality, we can pass to the generated ideals. So this is the same equality but as ideals. So we take the ideals generated by Z to the P is equal to the ideal generated by X plus Y times the ideal generated by X plus ZPY and so on. So why this is better? Because in this ring, for example, we don't have in general unique factorizations of elements. So it's not true that you can write any element as a product of prime elements in a unique way. But what is true is that we can write any ideal as a product of prime ideals in a unique way. So it's a standard technique to pass to ideals. So and we have this equality, and the ideal on the right. So these ideals are coprime. So since the product is the pth power, each of them must be a pth power of an ideals, of course. So X plus ZPY must be equal to ik to the p, where ik is some ideal of our ring. Okay, so things look still complicated, but if we go to the class group, so the class group is the group of fractional ideals modulo principal ideals. So this ideal is principal because it's generated by x plus zp to the k y. So this idea is equal to 1 in the class group by definition, essentially. So ik to the p is equal to 1 in the class group. So we have an element of a group whose pth power is equal to 1, but this does not imply that ak is equal to 1, because I mean there is no reason why if some element to the p is equal to 1, then the element should be equal to 1. And we would really like to have this ideal equal to 1, because if this idea is equal to 1, then this idea is principal, so we can go back to elements. And this is where regular primes enter the picture. So we say that node prime p is regular if p does not divide the order of the class group of the ring of integer of the cyclotomic field. Okay, why this is interesting? Because if p is regular, then since p does not divide the order of the group, there are in the class group, there are no elements of order p. So, but we have an element whose pth power is equal to 1. So since there are no elements of order p, this means that ak is equal to 1. Ik is equal to 1, sorry. So in practice, ik is a principal ideal generated by alpha k, that is some element in the ring. Okay, starting from this, it's not so difficult to prove the theorem, the so-called case 1 of the theorem, that is the following statement. So let p be a regular prime. So we consider the Fermat equation with this additional condition. So we consider the equation x to the p plus y to the p equals z to the p. But we also assume that p does not divide the product of x, y, z. And this equation has no solution in z. So I'm not going to explain the proof because it's rather technical, but it's a clever manipulation of this alpha k. So adding alpha k, the rest of the proof, it's not easy, but I would say it's rather elementary. It's not very complicated. But you see that we really need this condition about p, because otherwise we have ik that is an ideal, but we don't have any way to talk about elements, because the ideal is maybe not principal, and so we are stuck. Okay, so this is for the so-called case 1, meaning that we have this condition. But of course, we want to prove the full theorem, so we need a stronger condition. So we say that p is a strongly regular prime if it's regular and the following condition holds. So every time you have u, a unit in a z of zp, so this is the ring of integer of the cyclotomic fields. So every time you have a unit in the ring of integer of the cyclotomic field, such that it is congruent to an integer modulo p, then this unit is the pth power of a unit. Okay, so this is a technical condition that it's needed to prove the theorem in case 2. So the case 2 is the remaining one. So if p is a strongly regular prime, then the same equation as above, but now with the condition that p divides the product has no non-trivial solution in Z. Okay, so essentially, again, I'm not going to explain the proof, but as above, this is not the proof is not very complicated. It's rather a clever manipulation of it's a clever calculation in the ring of integer. But so as you can see in my title, there is no mention of strongly regular prime. This is because indeed we have the following lemma that a prime is regular if and only if it is strongly regular, meaning that this condition is automatically satisfied if P is a regular prime. And I guess that historically, this was the Kummer called a regular prime, a prime that is regular in our sense and such that this condition is satisfied. And then someone else, maybe Kummer himself, I don't know, realized that the second condition was automatic. But the problem with this second condition is that the proof of this lemma, I mean, it's called a lemma, but the proof is not so easy because the proof needs several ingredients. For example, I mean, there are several proofs depending on which definition you choose of regular prime, but using our definition, we need class field theory and also the class number formula. So it's really a big theorem to formalize. So what we decide to do is to introduce this notion of strongly regular prime and to prove the theorem in Lyon for strongly regular primes, and maybe later on focus on this lemma, so to remove this the strong regularity assumption. In any case, I think that at some point we really have to concentrate on this lemma because a corollary of the proof rather than the lemma is the following very easy characterization of a regular prime. So an odd prime P is regular if and only if it does not divide the denominator of any of the Bernoulli numbers Bk for k an even number less or equal than P minus 3. So one can take this corollary as definition of regular prime, but then I think that even to prove case one is a lot of work because at some point we really want to know something about the class group. So we prefer to take the other definition, the other condition as definition, and sooner or later we'll try to prove this corollary. A nice thing of this corollary is that this condition is very, very easy to check in practice. So for example, if we want to know if 5 is a regular prime, we just have to check if 5 divides the denominator of B2, and this is not the case. So the B2 is, we have a completely explicit formula for the Bernoulli prime, the Bernoulli numbers. So this is the Bernoulli numbers are even already in MATLAB. So this condition is extremely easy to verify in practice. And on the other hand, the condition about the class group is very, very hard. I mean, avoiding if one doesn't use this condition, verifying that computing the class number is a very difficult problem. So verifying the other condition it's quite complicated. So one downside of our choice of definition is that even if we will be able to prove the theorem, I think that we will not have any explicit example of a regular prime. So even proving that 3 is regular, that it would be quite a lot of work. This is true because the class number in that case is 1, so it's probably doable, but it's still a lot of work. So maybe at some point we will want to prove this corollary, because this corollary will give at once a lot of examples. So why this proof was interesting? Because historically this was the first one that worked for many cases at once. Indeed, as the case n equal 4 is treatable by hand, essentially if you choose a prime and you spend a lot of enough time on it, you are able to prove Fermala's theorem for this prime. For example, Euler proved the theorem for P equal 3, and I guess that in practice we were able to prove the theorem for any prime, for any given prime, but we were not able to find a proof that worked at the same time for all the primes. So a natural question is, okay, but how many regular primes are there? So here is the list of the first irregular primes, so the primes that are not regular. So you see that before 100, there are only 3 of them, 37, 59, and 67. Okay, so and it's possible to prove to treat these cases by hand. So we have the following conjecture that there are infinitely many regular primes. but unfortunately this is still a conjecture. We are even a more precise conjecture. We think we know the natural density of the regular primes. So the conjecture is that the natural density among the primes is e to the minus 1/2, meaning that around 60% of the primes should be regular. But let me stress that both of these statements are conjectured. We don't even know that if there are infinitely many regular primes. But unfortunately, what we know is that there are infinitely many irregular primes. So even if we will be able to formalize Fermala's theorem for regular primes exponent, there is no hope that this is enough to finish the proof. Meaning that we cannot just treat a bunch of cases of irregular primes and finish the proof. So at the end, to prove Fermala's theorem, one really needs some new ideas. Okay. So this is more or less the math I wanted to explain. So we are not going to dig inside the proof of the theorem, because if you are interested in number theory, you probably have already seen it, and if you are not interested, you are not interested, so you don't want to see it. What I'm going to explain is rather to show you some Lyon code. So and I don't want to cheat, so I'm going to show you the actual Lyon code we wrote about cyclotomic extension and stuff like that. So first of all, let me say what was already MATLAB before we started the project. So you see that we need quite a lot of algebraic number theory even to state to say what a regular prime is. For example, we needed all this theory about ring of integers, about unique factorization of ideals in the ring of integers of number fields. And this was already in the library thanks to the work of Banen, Damen, Narayaman, and Nuccio. So we already had a fairly complete library about Dedekind domains. In particular, we knew that for Dedekind domains, we had unique factorization of ideals. We also know that the ring of integers of a number field is Dedekind domain. Okay, and we also knew that the class group is finite. So this third statement, it's quite a serious theorem in number theory. So it's probably a first-year graduate student theorem. So it's not very difficult today, but it's not easy. It's not something you can prove. You have to know the proof to be able to do it. So we were very happy that this was already in MATLAB. And what was also in MATLAB was the theory about was the definition and some results about cyclotomic polynomials. So this is a nice thing because the definition of cyclotomic polynomials was my first contribution to MATLAB. And when I did it, I didn't have in mind this Fermala's theorem project. So at the end, it turned out to be very useful, but I did it just by chance. So what was completely missing was the theory of cyclotomic fields. So even the definition of cyclotomic field was not in MATLAB. And something that you learn when you start formalizing mathematics is that, okay, formalizing a theorem is difficult. Maybe formalizing a statement is easier, but formalizing a definition is very difficult, meaning that you really have to think hard about which definition you want to formalize. We usually have a lot of equivalent definition in mathematics, and we usually don't care which one we choose as definition and which one is true because of a theorem. But when you formalize it, this choice really matters, meaning that if you want to generalize a theorem, there are no problems. You have just to write down maybe a more difficult proof, but you can do it later. But if you want to change a definition, this can be really a lot of work, because now all the theorem you have already formalized are no longer work, and sometimes it's really a lot of work. So choosing the right definition it's a big problem. So let's consider the case of cyclotomic extension. So the informal definition, it's very easy. I mean, it's something like that. A cyclotomic extension is an extension generated by the roots of unity. Okay, so this is a nice sentence, but you see that it's quite vague, meaning, for example, an extension of what? Of fields, of rings, of, I don't know, something even more general. So of course, all these choice matter when you have to write down a precise definition, and we wanted a definition that was as much general as possible. So even if at the end in this project we are going to work only with cyclotomic extension of the rational, we wanted to give the definition that is as general as possible, since just because if maybe in 1 year someone else want to do something about cyclotomic polynomials in finite fields, we'll be able to use our definition. So we also wanted the definition. So we want the following. We want to be able to consider the following extensions. We want, for example, infinite extensions. For example, we want to be able to say that the extension obtained by adjoining all the pth root of unity to the rational is a cyclotomic extension. We also want to allow a positive characteristic. So we want cyclotomic extension of Fp, and you will see that this at the end will cause some troubles, because technically we also allow the pth cyclotomic extension of Fp. That is something we have to work with, but we will see. And we also need a ring extension, because we want to, I mean, at the end, all our proof will take place in this ring. And so we want to say that this is a cyclotomic extension. Okay, so we discussed a little bit amongst with the other contributors at the end. Sorry, I was forgetting about this. Even more importantly, we don't only want a general definition, but what we want is a characteristic predicate. So what this means? So consider this example. So this is a cyclotomic extension, meaning that we take the rational numbers and we add a primitive nth root of unity. So, and we take the subfield inside the complex numbers. So this is the smallest field that contains the rational. This is automatic, and the smallest field inside C that contains the rational and these roots of unity. So this is, of course, a cyclotomic extension. But we don't want to say that this is the nth cyclotomic extension of Q. We want to say that this is one nth cyclotomic extension of Q. Because if we now consider this one, so we take Q of X modulo phi n of X, so phi n is the nth cyclotomic polynomial, this is a field that is isomorphic to this one. So we also want to say that this one is a cyclotomic extension. But you see, mathematically, these objects are essentially the same because they are isomorphic as fields. So everything you can say using the language of algebra about this field will be true for this one, because the fields are isomorphic. So mathematically, there is essentially no difference between these two fields. But if we say to Lynn that the cyclotomic extension is this one, it will complain when we try to apply results about this one, because even if the fields are isomorphic, these are literally not the same thing. These are not the same set. So what we want is something like a predicate saying a given extension is a cyclotomic. So we never want to talk about the cyclotomic extension. So this is also something that you learn very quickly doing formalized mathematics, that you have to use these characteristic predicates everywhere. This is really important. Otherwise, I mean, working with them, it quickly becomes a nightmare. So at the end, the definition we choose is the following. So we take S, a set of positive natural numbers. I will comment later about this choice of n plus, but let's just suppose that S is a set of positive natural numbers. So we take A and B to types. So again, every time you see type, just read set. So this means that A and B are sets equipped with a commutative ring structure. So A is a commutative ring, B is a commutative ring, and B is an A algebra. So in some sense, B is an extension of A. So we want to say that B is S cyclotomic extension of A. So this is the definition. So we call it a class, but read definition. Class, it's used to because we want Lynn to be able to guess that some extension is a cyclotomic, but just read definition. So we say that B is an S cyclotomic extension of A is these two conditions hold. So the first one is that for any A in S, there is an element in B, there is R in B, such that the evaluation of the cyclotomic polynomial, the 8th cyclotomic polynomial is 0. So essentially here we are saying that for any A in S, we can find the root of the 8th cyclotomic polynomial in B. And the second condition is that, so the second, we want B to be generated by these roots. So the second condition is that for all X in B, X belongs to the algebra generated by the root of unity, the eighth root of unity where A is in S. So adjoint means subalgebra, the A subalgebra generated by, so the B in B such that there is A in N plus, there is A in S, such that B to the A is equal to 1. So X is in the subalgebra generated by this set. That is the set of root of whose order is in S. Okay, so just a small comment about this N plus. So N plus is the type of, so is the set of positive natural numbers. And we decided to, you see that we can write the same definition with S, a set of natural numbers. But we had the impression that if we allow zero to be in our set of, then essentially all our theorem would have started with, let's suppose that 0 is not in S. So since we are a little bit lazy, we decide to tell Lynn that S is by definition a set of positive natural numbers. Today, I'm not so sure that this was a good choice because it creates some problems. For example, you see that here we didn't write B to the A. We had to write B to the A in N. This is because even if mathematically a positive natural number, it is of course a natural number. In Lynn, this is not literally true. A positive natural number is a couple given by a natural number and the proof that this natural number is positive. So of course, Lynn knows that every time we have a positive natural number, we can coerce it to a natural number. So here we are obliged to say, take A, see it as a natural number, and then consider B to the A. So this is somehow when we know that natural numbers are not integers, but we never write this. In Lynn, for natural and integers, it works very well, but for positive natural numbers, sometimes it works not so well. So here we are forced to write this line that it is not very nice, but that's life, I guess. So in any case, this is the definition of cyclotomic extension. So, and you see that it is really a characteristic predicate. So we say that a given extension is a cyclotomic if these two conditions are satisfied. Okay, in any case, even if we have a cyclotomic, we have a characteristic predicate, we still want to be able to produce a cyclotomic extension of a given field. So we have the following definition. So we wrote it for just one number rather than for a set of numbers, but this is the same. So let's take K a field and N a positive natural number. Then we define the N cyclotomic field, the N cyclotomic extension of K as the splitting field of the Nth cyclotomic polynomial. And this line is just to tell Lynn that to automatically understand that this thing is a field and is also a K algebra. So we don't need to prove this fact. Lynn is able to guess them just because he knows that in general the splitting field is a field and it is also an algebra over the base field. And of course, we want to tell Lynn that this this cyclotomic field is a cyclotomic extension of K. So this needs to be proved. It's not difficult, but we have to prove it. But after this line, Lynn will automatically know that this extension is a cyclotomic extension. So it will automatically be able to apply all our theorems about cyclotomic extensions. So of course, I'm not showing you all the theorem we proved about cyclotomic extension, but we proved a lot of basic stuff. For example, that I don't know, a cyclotomic extension is automatically finite or stuff like that. And now after this line, Lynn is automatically able to apply all these theorem to this case. Okay. So this was for producing a cyclotomic extension of a field. But we also want to be able to produce a cyclotomic extension of a given ring. And here things are slightly more complicated because we cannot use the same trick because the splitting field is defined for a polynomial with a coefficient over a field. So what we did is the following. So we start with a ring A that we suppose to be a domain. We call K is fraction field. So again, you see that we are not saying that K is the fraction field of A, but we are saying that K is an A algebra, and that is essentially this means that it satisfies the universal property of the fraction field. But we don't want to say that K is the fraction field of A, because for example, if we are going to apply this for A equal to Z and K equal to Q, this is going to we can say that Q is the fraction field of Z, but maybe at some point we want to be we will not have exactly Q, but we will have something like Q of X modulo X. That of course it looks like the same as Q, but it's not literally the same object. So Q of X modulo X is not the fraction field from Lynn point of view, but it satisfies the universal property. So it satisfies these predicates is fraction field. So in any case, so we fix a fraction field, and we define the n cyclotomic extension of A as the subalgebra of the n cyclotomic extension of K generated by root of unity. Okay, so is the A subalgebra of cyclotomic fields n K generated by the element B such that B to the n is equal to 1. So this has the drawback that in practice, one has to write cyclotomic ring NAK, even if K is mathematically irrelevant. But I mean, it's just one character, so okay, we can write it. So it's not too much trouble. And of course, again, we have to teach Lynn that this extension is a cyclotomic. So we have this theorem, and you see that here there is one more assumption that this not equal 0 n. So here I'm assuming that n is different from 0 in A. So to be honest, I'm not completely sure this is needed. I will think about it this week, but this is the current statement. So in this case, it's surely true. But if n is equal to 0, I mean, cyclotomic extension behave in a weird way. So I'm not completely sure this is true, but it doesn't matter. I will speak about this not equal 0 condition later on. But in practice, this is for our project. This is of course satisfied because for our project, A will be equal to Z, so there are no problems. And we also want to we also teach Lynn that the cyclotomic field is the fraction ring, is the fraction field, okay, of the cyclotomic ring. Okay, so after these two lines, now Lynn is able to automatically apply all the theorem about cyclotomic extension and all the theorems about the fraction field. Okay, so this was the definition of the cyclotomic extension, and even if I don't want to enter into the details, I really want to stress that when we formalize stuff, choosing the right definition, it's really an important part of the job. It's not, we cannot just say this definition is equivalent to this one, and so who cares? This is not true. And Lynn really cares. Of course, we want to prove that maybe two definitions are equivalent, but choosing the good one, it's really important. Okay, now we are ready to give the definition of a regular prime. So first of all, we have to teach Lynn that the class group is finite. But as I said, this is not a lot of work, because in general, Lynn knows that the class group of the ring of integer of any number field is finite. So the fact that the cyclotomic field is a number field, it's very easy to prove. But what is missing is that the cyclotomic ring is the ring of integer. So you see, the cyclotomic ring essentially is the cyclotomic ring is by definition this ring. So it's the ring generated by roots of unity. But what we want is the ring of integers of the cyclotomic field. So the ring of integers is a number theory gadget that is in general bigger than this stuff. And so the definition is slightly less natural if you are not a number theorist. But let me just say that is something that is usually bigger, but is much better behaved than this one in general. I mean, in this case, the two are equal, but in general, we really want to work with this bigger ring than the one on the right. So we will concentrate on this proof in 1 minute, but given this theorem, the definition of regular prime is now very easy. So definition is regular prime. So we take P, an integer, a natural number. We suppose that is prime. So forget about this fact stuff. This is just technical thing. So we say that P is regular if P is coprime with the cardinality of the class group. So to be able to, so Lynn doesn't complain about this fine type card because he knows that the class group is finite. So if we write card, then Lynn we understand we'll understand that the cardinal is the cardinality of something is a cardinal. But here we want the cardinal as a natural number, so we write fine type dot card, and Lynn knows that this makes sense because he knows that the class group is finite. So you see the class group of what? Of the cyclotomic ring and the cyclotomic field. But here there is a weird thing that we wrote these curly braces and then php.1.pos. This is because you see that here P is a natural number. But as I said, the cyclotomic field is defined by a positive natural number. So here I'm saying that P is positive. And why is positive? Because it's prime. And I mean, 0 is not prime. So Lynn knows that prime numbers are positive. And so here I'm saying P and P is positive because it's prime, essentially. Okay, so this is the definition of a regular prime. And of course, we can also give the definition of a strong irregular prime. This is even easier, but so I don't want to show you this definition, but there are no problems in it. But what we are missing now is this theorem. That this is really, I mean, a not so easy result. So we are. I will tell this. I mean, I'm going to explain how we prove this in Lynn. So this is now in MATLAB since last week. So we have a nice timing. So what I'm going to explain is the proof of the following proposition. So that the ring of integers of the n cyclotomic extension is the algebra generated by Zn, but not really in general, but in the case of where n is a prime power. So first of all, this is enough for our project. Indeed, for our project, it is enough to consider the case where n is a prime. But as I said, we are trying to be as general as possible. And so, okay, one can say, okay, but here you are not as general as possible because this is true for any n. But the point is that the proof for any n uses the proof for prime powers. So even if at some point we will prove the proposition for any n, this proposition is still needed. So we are not wasting time. This is needed in any case. So first of all, I'm going to briefly explain the math proof. So we need two lemmas about number fields. So first, let's start with x, an algebraic integer. So first of all, the discriminant of q of x kills this quotient. So as I said, z of x is always smaller. I mean, it's smaller than the ring of integer because x is an algebraic integer. So this is a finite group, and it's killed by the discriminant is an integer, and the integer kills this finite group. We don't need to know that this group is finite. We just need to know that the discriminant kills this group. And also we need to know that if the minimal polynomial of x is Eisenstein at P, then the index of z of x inside the ring of integers is prime to P. Okay, these are two general results, classical results in number theory. And so we had to formalize these results in Lyon. But how we do we prove the proposition with these two results? So first of all, let's introduce epsilon n, that is 1 minus Zn. So here, recall that n is still equal to p to the k, so it's still a prime power. So first of all, we need that z of Zn is equal to z of epsilon n. This is completely trivial. I mean, mathematically, there is nothing to prove just because of this relation. And even in Lyon, this is very easy. Then the point of introducing this epsilon n is that we can use it to compute the discriminant of the cyclotomic fields, of the cyclotomic field. Of course, the discriminant does not depend on the choice of the basis we use, but we need to use a basis to compute it, and it's easier if you use epsilon n. So the discriminant of the cyclotomic fields it's plus minus p to the something. So the exponent really doesn't. The sign and the exponent doesn't matter. Don't matter. And also we need to prove that the minimal polynomial of epsilon n is Eisenstein at P. So this is not very difficult because we know the minimal polynomial of Zn, that is the cyclotomic polynomial. And in this case, the cyclotomic polynomial is just a geometric sum. So we make a change of variables, and then it's an easy computation to prove that the minimal polynomial of epsilon n is Eisenstein. Now, if we put everything together, so we are in this situation. So the index is prime to P. But you see that the discriminant kills the quotient, but the discriminant is a power of P. So putting these two things together, we have a group whose a finite group whose cardinality is prime to P, but it's killed by P. So this group is trivial. So this is essentially the math proof, and this is exactly the proof we formalized in Lyon. But okay, so I'm not going to show you all the proofs of these results, but I'm rather again concentrating on some definition. Even before we started the project, the discriminant was not in MATLAB. So we had the norm, the trace, but we didn't have the discriminant. So we had to define it and prove all its basic properties. And again, we choose to define it in a very, very general situation. So we take an A algebra B and iota an index set. So first of all, we need to define the matrix of the traces. So let B be a function from iota to B. So this is just a set of elements of B indexed by iota. And we get a matrix a square matrix indexed by iota, whose entries are the trace form given by B of I, B of J. So the trace form is the bilinear form that is non-degenerate if the extension is separable. So this means that this is the trace of the multiplication by the product of B of I times B of J. And as usual, the discriminant is the determinant of this matrix. So you see that to define the discriminant, we need to assume that iota is finite. because otherwise the determinant doesn't make sense. But here there is something weird. We have to write this classical exact trace matrix dot det. So I don't want to enter into, so I'm showing you the actual code, but the important part is just trace matrix ab.det. But this is because the definition of the trace matrix does not require, or maybe it requires, I don't know, classical logic. So we are telling Lynn, look, use classical logic here, because otherwise we got some troubles we don't understand. And so this essentially is a mathematician trick to avoid all this stuff about classical logic, excluded middle, and so on. So the interesting part is the discriminant is the determinant of the trace matrix.
Riccardo, maybe you need to explain what classical logic means. What we do, and non-classical logic means refusing excluding middle. And,
yes. Classical logic means using the excluded middle and the axiom of choice somewhere. So. Okay. So now we need some. We proved all the basic properties about the discriminant, and also essentially the most important one is that this one. So that if now we take an extension of field. So just let me comment that here I never assume that B is free as an A algebra, an A module. So we can maybe think that this doesn't make any sense, because to speak about the discriminant, we usually, to speak about the trace, we need to choose a basis. And so what happens if there is no basis? This is again something standard in formalized mathematics. We just choose some garbage value in this case. So in practice, the trace is 0 if B is not free. But the point is that now we are able to write trace matrix without telling Lynn, look, this is free because blah, blah, blah. Of course, in a lot of theorems, we'll have to assume it, but at least in the definition, there is no point in assuming that the module is free. But for example, here we are in the cases of fields, so of course, Lynn knows that L is free as a K module, because K is a field. So so I take an L an extension of K. I take PB a power basis. So what is a power basis? It's a basis as a vector space, but that is given by powers of a single element. So for example, in number theory, when we say K of X, we are going to use the basis 1x, x to the 2, and so on. And so we prove the following theorem, that the discriminant of this power basis, of this basis, is given by -1 to the something times the norm of the derivative of the minimal polynomial of the generator evaluated at the generator. So this is a standard formula about the discriminant, and essentially it's the formula that allows one to compute the discriminant in a lot of cases. So you see, in our cases, this will be quite easy, because we'll use as the power basis. We'll use the power basis given by Z. So the minimal polynomial is the cyclotomic polynomial, and we are able to compute this quite explicitly. Okay, so here n is just the dimension of L over K. Okay, so this is also, and we also need to know that the discriminant does not depend on the choice of the basis. So because indeed we will use Z to compute the discriminant, but we need epsilon, because the minimal polynomial of epsilon is Eisenstein at P. So we need to know that the discriminant of the basis given by epsilon and the basis given by Z are the same. And this is the following statement. So if you take a number field and two Q bases, then the discriminants are the same if the matrix that gives the base change has integral coefficients. Okay, so this is, these are standard results in number theory, and also the two general results were reasonably easy to formalize. I mean, it was quite a lot of work, but there were no surprises. And so now we are able to state our theorem about the discriminant. So we take a P to the K cyclotomic extension. So L is a P to the K cyclotomic extension of K. We assume that P is prime. We assume that P is not equal to 0 in K. We take any root of unity, any primitive root of unity in L. And we suppose that the cyclotomic polynomial is irreducible in K. So for example, this holds if K is equal to Q, and Lynn knows that. Then the discriminant of the basis given by our roots of unity is given by the following formula. That is the formula that I showed you before. I mean, even the sign is, here the sign is precised. And if you are familiar with this stuff, you can notice that usually this theorem is false, because it also works if K is equal to 0, and also if P is equal to 2 and K is equal to 1. And if you compute the discriminant, the sign is not good usually. So this is a weird thing, but I mean, this theorem is true in Lynn, but it's false mathematically in some sense. Why? No, because in Lynn, technically speaking, if 1 divided by 2, if 1 and 2 are natural numbers, 1 divided by 2 is 0, and 0 minus 1 is equal to 0. Because you see, of course, in Q, this is 1/2, and in Z, this is -1. But in N, for example, this 1 cannot be equal to -1, because -1 is not an element of N. And in formalized mathematics, we really want total functions. So we really want to be able to write 4 minus 2 equal to 2 in N. But if we want to be able to write this, then Lynn wants to be able to write 0 minus 1. If we try to introduce partial function, this is it gets really complicated. So it's better to avoid it. And the standard choice is to just choose a garbage value when the function is morally not defined. And here it turned out that the garbage value were the good one. So now this theorem in Lynn is true in general.
Yeah, to punish you for mentioning your little tricks, I'd just like to mention that your time is essentially over, so you can go.
Yeah, so yeah, 2 minutes. Yeah, I just want to show just one last thing. So now with this computation, we are able to prove the final result. That is that the cyclotomic ring is the integral closure of Z inside the cyclotomic field. So this was easy to prove. I mean, easy. It was like in the math proof. And just to show you, so I will not have time to talk about this not equal 0 class, but I want to mention at least that sometimes things get complicated. For example, here we encounter the so-called characteristic 0 diamond. So what is the point is that now Lynn knows that this field is of characteristic 0 because it is an extension of Q. But so, and Lynn knows that any field of characteristic 0 is a Q algebra automatically. And he also knows that this is a Q algebra because the cyclotomic field is always an algebra over the base field. Of course, mathematically, there are no problems because these two Q algebra are the same for the very good reasons that any two Q algebra structures are the same. But Lynn is not able to automatically understand that these two algebra structures are the same. And so it complains with very frustrating problems, like maybe sometimes he asks to prove that 0 is equal to 0, but this is not automatically true because the two 0 are not in the same algebra structure. So here we have to use this ugly hack. So here we had to use this line telling Lynn, forget that the cyclotomic field is an algebra over the base field. So just use one algebra structure given by the characteristic 0 thing. So this was just to show you that this is the kind of frustrating problems that still exist in formalizing mathematics. Of course, we are working to avoid all these problems. Sometimes we are able to do it, but sometimes not yet. So this is an example, and the not zero class is a similar problem that I don't have time to talk about it, but it's this kind of problem that mathematically are irrelevant, but when you formalize stuff, you very often encounter them. And so I think I'll stop here. Thank you.
Other questions?
So, Riccardo, can you maybe comment a bit on how far you think that you are with the project?
Yes, sure. So now this thing about the ring of integer is done. So now we still need some general results. For example, I think that the next main goal is to prove that if an algebraic integer has all its conjugates that have norm equal to 1, then the algebraic integer is the root of unity. And then we have to develop a little bit the theory of cyclotomic units, and then the proof will be essentially done, because the proof is really not. I mean, the case I'm talking about, the case one. The proof in case one is not very difficult once one has all the ingredients.
So are you 3/4 done?
Case one, I would say maybe yes, 3/4. Yes.
And Riccardo, can you say something? So at the very beginning, you mentioned the option of considering infinite cyclotomic extensions, but as far as I've seen, you've always taken n to be.
Yes. I mean, so you see in the definition there is this set S that can be infinite, of course. So.
Okay. So you can take, for instance, all the powers of p.
Yeah. You can take whatever. I mean, and of course, the basic API about cyclotomic extension is done for any S. So all the very basic results are true. I mean, are ready there for any S.
Very well.
I mean, but these are really basic stuff, like the fact that it's a field and stuff like that. But if S is infinite, it's not even a number field, so it's rather orthogonal to our project, I would say.
Yeah, but it's good that they're already there. So that the ones who want to do it without a theory,
that was my point. Maybe there are results that are missing, but the definition is there. So if you want to consider infinite cyclotomic extension, you surely need to prove something about it, but you don't have to change the definition.
Right, thank you.
Other questions? Can you say just a little bit what happens if you allow 0 to belong to S?
So to be honest, I don't know, but I don't remember exactly, but maybe that anything it's cyclotomic, or maybe nothing it's cyclotomic, something like that, because
okay, yeah, you would need to change the definition of adjoint roots to forbid A.
Yes, exactly.
But if you make the obvious modification of the definition, do you still see problems down the road, or not?
No. I mean, of course, the definition. No. I don't think that there are mathematical problems. So it's just that at the beginning we thought this was less convenient. So, and because the theory looks like, I mean, the theory of cyclotomic extension, it's in some sense multiplicative on this S, and so we thought it was more natural to take S set of positive numbers rather than natural numbers. But I don't think that to be honest, I'm not sure. I'm not sure anymore. It was a good choice, but I think that allowing 0 will make something easier. For example, here we can write B to the A, but it makes something else more complicated. So to be honest, I don't know. We should try the refactor, but I'm too lazy to do it.
There are no more questions. Let's thank Riccardo again.